Okay, so let us begin. Welcome everyone to the first meeting of the Integrable Systems seminar of the spring semester. And it is a great pleasure to have here Paul Zinn-Justin from the University of Melbourne, who will talk to us about generic pipe dreams, lower upper varieties, and Schwartz MacPherson classes.
Okay, I didn't remember the exact title, so I improvised, but I think it's close enough. Yes, thank you for the invitation. So, I mean, these are ideas I've been toying with for many, many years. I wrote a bunch of papers which has some related content. This particular thing that I'm going to show you is actually part of a paper that we're currently writing with my collaborator, Alan Knudsen, but it has ideas coming from other papers that I wrote with other collaborators. And so let me start with the lattice model. So this is going to be a story about lattice models. So good old solvable lattice models from, well, originally from statistical mechanics, though my interest in them has very little to do with the physics, but very much to do with the algebraic networks and algebraic geometry. So I'll show you the model, and then I'll tell you why I care about it. Right, speak louder. I could put it higher if you want. I don't know if I can speak louder. Okay, let's try again. Is it better? Yes, no, maybe. Okay, let's try. Okay, so here's the rules of the game. You start with a lattice, like a square grid, and it has some height, some width m, and some width n and some height m. And for no particular reason, I'll choose m less or equal to n. It's not crucial. Otherwise, you can switch them. And I'm going to draw pictures. But for that, first, I have to tell you what the boundary conditions are, and then I'll tell you how to fill. So we're going to fill this grid with pictures, and I've shown you all the possible ways we can fill them, but there are some rules. So first, the rule is that there's going to be a bunch of red lines, and they're all going to come out somewhere at the top. So I'm going to give you an example. Maybe they come out here, and they are going to come in from the sides. And the rule is that on each row, there's exactly one red line coming in, and it can come in either from the left or the right. So for example, maybe there's one line coming in from here, one coming in from here, one coming in from here. And then these lines have to propagate somehow within the lattice. And the rule is that if on that particular row, the line comes from the left, then it kind of has to go, it has to kind of propagate northeast. So it has to propagate this way. And if on the contrary, it came from the right, then obviously it has to propagate this way. So we're going to use tiles from this row. And then the rule is that you're supposed to fill every square of this lattice with one of those pictures. Of course, you can leave it empty. That's always an option. Don't worry yet about the B's and A's and X's. They will be weights we'll put on them. So I don't know. I'll choose a random example, which is the same one as in the paper. So maybe this line is going to go all the way here. And maybe this one will go like this. And maybe this one will just go like this. And you can check that all the rules that I've said are correct. On these rows, they kind of go southwest. On these rows, they go southeast. On this row, they go southwest. And that's about it, right? So let me summarize what the data is for such a picture. First, you have to decide for each row whether the lines are going left or right. So that means to each such picture, you can associate a binary string, which tells you, maybe I'll use it. I'll use those symbols that I have here. So in to the power m. So on the example here, that means let's say we read from top to bottom. So the first row is going northeast. So in this case, it would be going northeast, then northwest, then northeast, let's say. So this is this example. So for each row, you have to decide whether the lines are going right or left. And the other interesting data you can read off this picture is there's still some choice where the lines come out at the top. So I want to also associate to this another data, which is, so this I'm going to call beta. Did I put a beta? No, beta. And then I can associate what I call the connectivity of this picture, which is something that's familiar to anybody that's played with such pictures, in particular played with pi dreams. So pi is going to be, let's see, it's going to be a map from 1m to 1n. And it's going to be telling me which path ends up where. So I'm going to number the path in the following way. I'm going to number them clockwise around here. So that means I'm going to number them this way. So I look at all the places where they enter and I follow clockwise. And then I look at where they exit on the other side. So that means here, in this example, pi is, so beta is this thing and pi is, so the first one exits at the fourth location. So I'm going to read from right to left. So it's going to be 4, 1, 3. Yeah, if I haven't made a mistake.
Sorry, can you explain numeration?
Yeah, so I'm reading the, I'm just labeling the exits on the left and the right clockwise. So I start from top to bottom on the left, then there's nothing at the bottom, and then bottom to top on the right. It does seem a bit weird, but that's the way it goes. All right. All right, so now I define, so this is an example. Of course, now I'm going to define a partition function. So I'm going to define z sub beta and pi for fixed beta and pi of the form that I just showed you. So we fix beta and pi, we fix the binary string, we fix the connectivity, and we say we sum over all these configurations. So all configurations with such with you know, which map to beta and pi, let's say, under this map. And I'm going to give a weight, and the weight is, so that's the part that's written here. The weight is going to be a product over I equals 1 to m, product of j equals 1 to n. So it's a product over all the elementary squares of the lattice. And the, so it's going to be the weight at ij, if you want. And so the weight you can read off on this, on the blackboard here. That means each time you have a blank, so yeah, you have to be a little bit careful. Okay, so for example, each time you have a blank, let's give an example here. This blank is going to contribute, so you have to look up on this table. It will depend whether it's going right or going left. So it's going right, so you have to look at the first row. And so it's telling you that it's supposed to be b minus xi plus yj, but I haven't told you what I and j are yet. So xi, I is the numbering of the labeling of the row. So here it's 2. And y is the labeling of the column, which is just a standard labeling from left to right. Right? And so all the bands are always contribute a plus b. So this is going to be some element of z, a, b, x1 dot 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 xm, y1 dot 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 yn. And yeah, so all the bands are always going to contribute the same, but there's a funny business about the fact that these weights are switched. There are only 2 other types of weights, but you know, so these have the same weights, these have the same weights, but they get switched depending whether these are rows where things are going leftwards or rightwards.
Sorry, can you teach me why it's third column?
Right. So again, I'm doing this funny business of relabeling the rows in a non-standard way. So this is row 1, this is row 2, and this is row 3.
Okay.
So this is the row index, so the row label. And this is the column label. And this one is just from the usual numbering from left to right. Right. So this like a 1, 2, 3, 4. So this is 2, 4. Oh, sorry.
Okay.
My mistake.
Okay.
Thank you.
Thank you.
Yeah, that's good. All right. So I'm not going to write you the full expression for this particular configuration, but you could in principle. It has, you know, in this case, 4 times 3. So it's going to be a polynomial of degree. Yeah, we even know the degree of degree n times n. So.
Sorry, and you show that there is 2 options between blank buckets.
So, sorry, say it again.
There's 2 options between buckets.
Well, I mean, for each row, you have to decide whether you use these pictures or these pictures. So effectively, no, there's only one choice of blank. for any given row. These are the pictures allowed when things are flowing to the right. These are for different rows, right? The choices are for different rows. So maybe I should have said it again. So this row is like flowing this way. This one is flowing this way. This one is flowing this way. And so for each row, you have to choose one of the tiles of the corresponding row. So there is effectively only one blank, but the point being that they get different weights depending on whether they're on the right going row or on the left going row. Okay, so now comes a little, I don't know if it deserves the name of theorem, but I'll, maybe let's put it as a proposition. Z beta pi is actually independent of beta. So this is something I find myself a while ago while playing around, and then it turns out there's actually some literature on that. There's a very similar result, but it's yeah. So let me add that this is a result which generalizes some work by Knudsen and some co-author. I don't know. They have something similar to that. It's not exactly that, but it's kind of in the same spirit. And in fact, the proof I find for this result is very similar to their proof. Sorry, I forgot to. Probably the references in the paper we're writing, because immediately when I showed him this, he was like, "Yeah, I know this type of result, but no, we don't have the references." Sorry. Anyway, so yeah, so there's this kind of weird, surprising fact that actually this doesn't depend on beta, and the way there are two questions here. Well, there are three questions: how to prove this, how did I even come up with such a conjecture before proving it, and more importantly, what do we care, right? So I want to show you all these things. I want to give you first a quick proof of this result, and then I want to tell you a little bit to the motivation where this comes from, why I even got to the conjecture of this, and this has to do with the geometry. All right, so okay, so first a little bit of yeah. So first the proof. So we'll have to work a little bit to do that. So that should already take us a little while.
Can you just for understanding? Consider the case when you have only one row and the beta have only two options.
Exactly. So we'll definitely talk about one row. Yeah. So do you want to do this now, or it will come as part of the proof? We'll have to analyze the. In fact, let me tell you how the proof is going to go. That might answer your question. So the proof is going to. We do it in two steps. We're going to show. So the first step is precisely what you're going to say. We're going to show that if you have z beta 1 dot beta m minus 1. Okay, so I had colors at some point. I might have to, maybe I'll skip the colors for the errors. We'll show this part. And so effectively, that will in particular do the case of one row. And then we'll show that when you have, let's say, beta prime, well, beta 1 dot beta r, and then this. Sorry, and then beta prime 1 dot beta prime s2. So you can switch basically this way. So the proof consists of the following two facts. First, we can switch two of them, and second, we can arbitrarily flip the last arrow. And it's not too hard to convince yourself that any two binary strings can be obtained from each other by one of these two transformations, by a sequence of such transformations. You know, it's. Right, so let's do one first. So that's the easiest one. In this case, it's actually bijective. So it's not interesting from my perspective. Bijective proofs are boring. They don't actually use any of my fancy technology that I like. So yeah, so one has a bijective proof. So all we need to do is basically massage a bit the last row. So let's take the example we had here. So all we're going to do is the bijection only modifies the last row, and this is what it does to it. So it takes, so maybe now I'm going to put some colors back. Be careful not to step on this. Yeah, but I want red because I used red for the. So for example, here we had this picture here, like this, and the way you should think about it is you basically. You know, at the bottom, basically, there's only one path, and all you can do is basically do something like that. And so all you do is send it to the other one, which is this thing, right? So that's really boring. So, in physics, I kind of want to think of this as something called crossing symmetry. It's not obvious why it has anything to do with crossing symmetry, but for the people who work in integrable systems, maybe they'll recognize that secretly this is crossing symmetry for some SL2 model. But it's a bit kind of hidden. And clearly this is, in evolution, you can do it, you can pull it back this way. And you can see that the weights are exactly going to be preserved because this one is always going to contribute A plus B. So when you do that, another important thing is you don't change the labeling. The 2 here will move to the other side. So also labels of rows are unchanged. So that's nice. Unchanged. And so here this A plus B is still A plus B. This one used to be, so it was used to be A plus xi minus yj. So in this case, A plus xi minus y1, let's say. And this is also A plus xi minus y1, conveniently. And so on, right? So this one is B minus xi plus y3, maybe. And this one is also B minus xi plus y3. So of course, the weights have been chosen in such a way that this bijection is weight preserving, right? So I should say weight preserving bijection. By weight, I mean this contribution to the partition function, so this product of, this thing here, right? So that's kind of boring, actually. It's an obvious bijection. It preserves the weight, so clearly that is true, that this property is true, basically. I think we can all agree on that. Okay, now comes 2. 2 is much more interesting. Because it's non-bijective, you can actually check in some explicit cases that, so maybe I should have said that, sometimes you can check that the number of configurations does depend on beta. So in other words, it's not a term-by-term identification in general. There will be some non-trivial recombinations. So it's only the whole sum that's invariant, that independent of beta, but the actual summands may differ, and we'll see that in proof number 2, which is non-bijective. Okay, so what is the proof of number 2? We have to, of course, use the Young-Baxter equation. So let's do that. So I'm going to introduce lozenge tiles. If I had more time, I would have drawn them. So I'll draw them here. I should have done that earlier. There's also 7 tiles, so it's not that bad. So they kind of look the same as these, but now I'm going to draw them as lozenges. So 1, 2, 3, 4. No, 2, 3, 4, 5, 6. I'm going to miss one. Okay, fine. There'll be an extra one here. And they all have weights. So I'll draw. So they kind of look. They are the same principle. So there are these, and then there's the crossing and the like this, and the difference is now the weights are going to depend on 2 parameters, xi and xj. So as usual, all of these have weight A plus B. That's not changed. So these are the ones where I have to be more careful. It's xj minus xi. And this one then has to be A plus B plus xi minus xj. Sorry, so the last one I'll put here. Okay, so this is just a definition. Now, what is the actual statement? So we need this little lemma. So we're going to draw, there's going to be 2 squares, but of course the squares, I'm going to slightly deform them into also rhombi. And so we're going to get this kind of picture. Okay, so this is not very instructive, so I have to tell you. So these are, so we have to decide which one is which. So maybe this one goes this way, 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 and this is the new one, which I just introduced. Okay, so what does this lemma mean? It means for all connectivities of the external edges of a hexagon. So this is an identity which is true. So for all connectivities of the boundary points of the hexagon. So there are 6 of them. So there are quite a few different ways these points can reconnect. And the rules of the game are you're supposed to sum all the configurations in there where this is filled with one of those pictures here. This is filled with one of those pictures here. And finally, the lozenge empty one has to be filled with those ones. I guess you could also draw an arrow here. You could say these go kind of straight to the left, I guess. So maybe I'll put it this way. So this is straight to the, I see the problem. No, maybe I'm not going to do that. Sorry. I screwed up my conventions and now I can't do that. Okay, let's just put it empty. It's fine. It doesn't matter. All good. Yeah, that's interesting. I messed up one of my arrows. Oh, it's okay. It's fine. Okay, so let me just give you an example to see what this equation actually means in practice. For example, that means suppose you have a connectivity. So example. Oh, and I also forgot to say, so the weights are going to depend on one parameter yj here, and two parameters xi, also now xi and xj, indices, so yk maybe, yk, xi, and xj, and I'll tell you in a minute what exactly I mean by that. So let's take an example of this identity. Suppose you look at all the configurations in the hexagon that connect, I don't know. So I'm just going to follow the same example as in my notes, otherwise I'm going to screw it up. So let's say like this. So you look at all the configurations on either the left or the right such that you can realize this connectivity. Okay, so you try. So there's not going to be a lot of them. So I think I chose this example to be relatively simple. But let's do the exercise in real time. So for example, this one could go like this and then straight out. This one could go like this and then straight out. And I think on one of the sides, that's all you get. Yes. And on the other side, there are, I think, two possibilities this time. Okay, and on the other side, as I just said, I think there are two possibilities. Either it goes straight like this, and no, wait. This one goes like this, or this one goes like this, and this one goes like this. If I didn't screw up, let's see if my pictures agree. And for each of them, you're supposed to compute the corresponding weight. So for example, for this one, if you compute carefully, you get a plus b squared. So the bands are always easy. So the only one complicated you have to compute is this one. And so you have to look up in the table. And that's a plus xi minus xj or something like that. Yeah, x plus xj minus yk, I think. All right. And this one has maybe a plus b times something, plus a plus b times something. And okay, my computer keeps dying. It's annoying. Oh, it's also a plus b squared, sorry, xj minus x. And then here you have xi minus yk, I think. Yeah, so in this case, it's particularly, and it doesn't work. I forgot something. It's a plus xi minus yk, sorry. Yeah. Right, so if you check carefully, you compute the weights, and you check that they're the same on both sides. But you can see how you have some interesting recombinations going on. Not terribly interesting here, but there are more complicated examples. I just don't want to do it on the board. Right? So the claim is that if you choose any connectivity at boundary points, you'll have such an equality. And now the proof, so now we're going to use this to prove lemma number 2. It's a classical type of proof, which we always do in a solvable model. This is this unzipping argument. So we're going to focus now. So we're going to have a bunch of rows which are spectators. And there's going to be 2 rows where all the action takes place. And it's all about, you know, it's our favorite Young-Baxter algebra, basically. So we're going to check very carefully what the Young-Baxter algebra is in this case. So these are the 2 rows of interest. So we start with a configuration, maybe, I don't know. So we're going to apply this one to maybe to the left. So it's going to be, okay, so let me draw an intermediate one. And so there's a line coming from here, line coming from here, and we want to somehow turn this into, at the end of the day, we want the same picture, but where the 2 lines are coming out in the opposite fashion. So the line will be coming out from here. Oh, sorry, I'm doing the same again. From here to here, right? Okay, so we want to show, and all the rest is the same, basically. And we want all these transformations to preserve the connectivity, which of course is the case of my little lemma. So it's implicit here that we fix the connectivity, and that's it. Okay, so the way we do it, so each time these squares are rectangles are going to remain the same. So the first thing I'm going to do is say, if I introduce an extra lozenge here, I'm going to do it in such a way that I'm going to force the line to enter from here. But you'll notice that if a line, I already screwed up. That's a brilliant. I wrote you completely wrong. Yeah, that's what happens when, sorry. A mistake, all these are completely wrong. I went too quickly and just drew the, well, it's better to notice it now than in the middle of my proof. Well, it is the middle of the proof, I guess, but anyway, sorry, all wrong. That is interesting. I managed to completely screw up the proof. Sorry about that. So that means this lemma was also wrong. Okay, I'm going to erase this as well. That means probably this calculation was also wrong. I'm not sure. Sorry, I got the weights wrong. I messed up two different. Okay, let's go back to. Sorry, this is not how it's supposed to be. Okay, so we're going to redraw all the pictures correctly now. I basically rotated by 90 degrees all my lozenges. This is the problem with working with a manuscript that's still very much a work in progress. Even though here we go, sorry. Much better. So you can check again that the lemma is correct. I just screwed up. The example I gave you was a non-example. So you have to redo the example correctly. Apologies. But because here it's crucial to understand here my point is as follows. If you impose that there is a line coming in from here, but no line coming in from here, if you look at those pictures, there's a unique way this can go. This is the only possibility on the left. If you have something, oh no, wrong one, sorry. Oof. I'll blame it on, I can't blame jet lag because I'm not really jet lagged. We're on the same longitude in Australia. Sorry, it's this one. Right, so if you have a line coming in this way, the only thing it can do, it can go only straight like this, right? And there's no other option. That's because all these options would imply that the line goes out somewhere else. And now I have to give you the weights, of course, which I haven't rewritten. Let's do that really quickly. So the weights are kind of similar. They were basically right before, but so let's redo them quickly. So A plus B plus, yeah. Apologies. And the last one is xj minus xi. Yeah, so these two weights were also exchanged in the process. Okay, good. So I introduced this extra thing, and it doesn't really matter. All you have to incur is the fact that you have this weight of A plus B plus xi minus xj. So how about I just put it in the denominator? It doesn't really matter. Xi minus xj. And then all the rest is the same, right? And now I apply repeatedly the Young-Baxter equation, which makes me move my lozenge all the way to the right. And so now I have this picture where things are now a little bit curved like this. And now I have my lozenge here. And I forgot to mark also the boundary here was like this. So now I have something like this. And now this is on top. Yes, this is correct. And finally like this. So after applying repeatedly the Young-Baxter equation, you get a picture like this one. And again, now you look at the possibilities for the lozenge. And you find that, so now this time, it's what I was saying earlier, the only possibility now is this one. It can only go straight. There's no other option here. So it has to do this. And there's still a 1 over A plus B plus xi minus xj. But now, surprise, the weight of this thing is the same as the weight of this thing. And so it cancels out nicely. And after redrawing this picture slightly, you get this picture. And that's the same picture as the original one, except those two rows have been switched.
argument like in the end have only this possibility.
Yeah. So that's crucial. That's you know that's you know this is a kind of a trivial case of the Young-Baxter algebra where when you commute you only have one term basically. And well, you could just look at the pictures. You know, if you have something, so I'm fixing, say, this one and this one to be occupied and empty. These are the only possibilities. This is occupied, occupied, empty, 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 occupied, occupied. This is the only option that has occupied, empty. Yeah. Okay. The other good news is that the labeling is actually not really changed when you do this. You know, when you move these two lines, because we're labeling kind of clockwise, it also preserves the labeling. It modifies them in the obvious way that you know the label of the lines kind of follow the motion. Basically, it's a bit hard to say in words properly, but trust me, the labelings, which in this case corresponds, you know, these are the two labels of the two rows. They nicely exchange in the way you would expect, basically. Right, so at the end of the day, this was exactly, if you do the summation of all these diagrams, this is exactly Z. Well, it's the left-hand side. It's like beta 1, dot, 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 beta R. And then, you know, this, and then all the other ones. And this is exactly the one where it goes the opposite way. So Z, beta 1, beta R. No, okay, so as I said, I think I put my errors, yeah, all my things going up. So that's fine. And then beta prime, right? So effectively, you've done exactly what you wanted. You've switched two labels in your binary string. So that proves number 2. All right, so that's end of my little proposition. Yes, okay, so now I want to tell you why I care about such things. We're going to change gears. Sorry, I'm thinking which. All right, let's erase the beginning of the proof. So a long time ago, my collaborator, Alan, for completely unrelated reasons to anything that is of interest to me, introduced a certain algebra geometric object. And it turns out to be closely related to this lattice model. So let's do that. So define. This is a slight generalization of what Alan defined, but he only did the square case. We're going to do the rectangular case just because we can. So he only did n equals n, basically, but it doesn't really matter. It's
you start this one configuration and put this we obtain 20 configuration. But if you sum up, then you have.
That's right. So this identity is only an identity true when you're summing over all the configurations, because yeah, so everywhere kind of implicitly there is summation over all the configurations which have those boundaries, basically.
This work is on the single configuration. Then go to the right.
Yeah, so one can correspond to many. It's not a one-to-one. That's why I'm saying it's not bijective. It's a many-to-many correspondence. And you know, I mean, my whole business, a good part of my life has been applying ideas from integrable systems to combinatorics. And you know, if the proof turned out to be bijective, then probably combinatorials would have already found it before me, basically, because that's what combinatorials do. They do bijective proofs. So if I want my proof to be interesting and new, it has to be probably non-bijective. Otherwise, there's a good chance that it's not interesting. So this one is most definitely non-bijective. And in fact, I mentioned the fact that this generalizes a result of Knudsen and collaborators. Their proof was bijective, and it was a very special case where things are bijective. So in that sense, the result generalizes, but not the proof, you know, because their proof is very much bijective as far as I understand. All right, anyway, so Alan again, so the same Alan Knudsen, introduced many years ago, more than 20 years ago, again, up to the fact that he did it in the square case. So let me just get my notations right. So I want x to be from m to n. Okay, so x to n. So so these are, so n by n m by n matrices, and so pairs of x. Okay, maybe let's put it this way: x, y in mat like this cross mat nm. And yeah, all my varieties are over the complex numbers. I'm not going to write it. This is just a affine scheme, nothing to worry about. And again, let me check the conventions. I want xy to be lower triangular. And yx to be upper triangular. Okay, so x and y are rectangular matrices, but they have the nice property that their shapes kind of are transposed of each other. So it makes sense to take the product either way, and you get square matrices. And I want them to be weakly triangular. It doesn't really matter which way. I prefer lower upper. In the original paper of Alan, it's upper upper, and he calls that upper upper scheme. But I'm going to call that the lower upper scheme because I like it better this way, by my own reasons. And clearly, in this geometric picture, it's clear that M and N play symmetric roles. You can switch them; it doesn't matter. And so I might as well again assume that M is less or equal to N. Okay, so I want to give a name to this set. So pi, I'm going to say that, I'm going to define SMN to be the set of injective maps from, maybe I should have written it at this stage. So injective maps from, yeah, this I should have said is always injective. So from 1M to 1N. So let me just give a name just for no particular reason, but yeah, okay. Just so I don't have to repeat each time. Let pi be an injective map from blah, blah, blah. All right, and then, so we know a lot of things about this lower upper scheme, at least I do. So for example, here's a proposition which, again, generalizes work of Alan. The irreducible components of E are indexed by SMN, by such permutations, by injections by SMN. And you can give them in various ways, but the way you should understand, let me write the formula and then I explain, is very intuitive. Sorry, my computer keeps switching off. It's not happy because it doesn't have any power. Right, so there are two different ways you can do it, but they're kind of all, yeah, let me just give actually one of them. So x, y, y, x. So once again, x, y, y, x. Yes, yes. Then I'll explain why this is intuitive. And I have to reload R. And you can take the closure for your favorite topology. I don't care. So what's going on there? Well, there's something really interesting going on. You have x, y, and y, x. So these are two matrices of different sizes, but they're, you know that their spectrum are closely related to each other. You know that this, so let's say M is less or equal to N. So then, I don't know, x, y is M by M, and y, x is N by N. So it's bigger. But the point is that you know that the spectrum of yx is simply the spectrum of xy and a few more zero eigenvalues. This is good old linear algebra, right? So the spectra are quite closely related. So if we only care about non-zero eigenvalues, they are the same. They have the same non-zero eigenvalues, let's say generically. So the bar here is precisely to ignore all subtleties related to non-generic behavior. Let's just say generically, if you assume xy to be invertible, then yx will have the same rank. M, and then you'll have a bunch of extra zeros as eigenvalues. But these matrices are triangular. So their eigenvalues are actually on the diagonal, right? So the way you should think about it, so you have xy, which is something like, suddenly it's the lower triangular one. So it has some eigenvalues, lambda 1, lambda m, 0, star, star. And then you know that yx is going to have the same eigenvalues also in the diagonal. So they're going to have to be permuted in some way. So there'll be some zeros, and then there'll be like lambda, I don't know, lambda 1 somewhere, lambda 2 somewhere, and so on, right? And so when you think about it, you realize that there is some combinatorial data which tells you where the m eigenvalues land on the diagonal of yx. And that's exactly given by an injective map from 1m to 1n, right? And so generically, that's exactly all that's going to happen. You're gonna have components that are determined by the choice of that permutation. And then of course, there are degenerate cases where the eigenvalues collide, and then weird things can happen. So we're not going to worry about that. We're going to assume that everything is distinct non-zero, and then we're going to take the Zariski closure and whatnot. Right? So that proposition, is only slightly harder to prove than, well, it's a bit more work than in his original paper, but you can do it. So now let me give you two versions of a strong version and a weak version of the theorem. So first, the weak version, the direct relation. Oh yeah. So maybe I should say a few more words about. Sorry, no, one more word before I introduce the. So this variety has a big group acting on it. I should have said that from the start. So GLM. No. Let me try again. Let me introduce, so let me check the notation, because I have this mental block in my head. I never know when plus is supposed to mean upper triangular or minus is supposed to be upper triangular. I've never understood the convention. For me, there's nothing plus or minus about it being lower or upper. But anyway, so let B minus be the set of invertible, so lower, so M by M lower triangular matrices. And let me define B plus to be the set of invertible N by N upper triangular matrices. And you can see that very naturally, B minus cross B plus acts on E. Well, it acts on the whole space of matrices, but particularly it acts on E by the obvious thing you want to do. You want to do X. There's only one thing you can do, basically. So, so if you take an element here, UV, so X has to go U X V inverse, and Y goes to V X U inverse. Yeah, there's an obvious action, which is on the left, on the right, and it preserves those equations here, right? Of course, we don't really like Borel subgroups. We like things which are reductive. So how about we just restrict to the Cartan in there? So in particular, there's a T minus cross T plus sitting in there, which are just the diagonal matrices, right? So let me just do it this way. These are just the diagonal matrices. And here, the minus or plus only refers to whether they're size M or size N, but it doesn't matter, right? So we're almost there. So now, so what does it mean? Well, it means a variety, depending on your background, whether you're more into geometry or combinatorics, one way or another, it means I'm going to be able to associate a polynomial to this, to each such variety, right? So let me give you maybe the geometric version. I usually give the more combinatorial version, but I fear that I wasted a bit too much time on messing up my proofs. So maybe I'll give you the geometric version. Is that you can then consider equivalent cohomology T plus cross T minus of whatever, the ambient space, whatever it is. That ambient space is just contractible. So this is the same as the cohomology of the point. So this is nothing but just the ring of polynomials in a bunch of variables, as many variables as the rank of the torus. And of course, I'm going to use as a name this x1. Oh, and I forgot the scaling. Sorry. Also, you can also scale independently x and yeah. So also C star cross C star also acts on E by x goes to alpha x and y goes to beta y, where alpha beta live in there. Right. So actually, you have a torus of a dimension of a rank m plus n plus 2. Right. So I missed my C star squared here. Okay, here we go. So now we have we want as many variables as the rank of the torus. So that means we're going to have X's, Y's, and obviously A and B. A and B, sorry. Right, so what it's telling you is that, like, so that's one way you can do it. Of course, you have completely combinatorial description of how to compute inside this ring. But let's just say that in particular, you can define the class of E pi inside this ring, whatever. H. Yeah. And so what's the main theorem? Well, one of the two theorems. The other one's supposed to be the connection with Schwartz, MacPherson classes. I don't know if we're ever going to get there. But anyway, one of the theorems. So the weak version tells you that, oh yeah, by the way, the degree of the class, yeah, I haven't told you the dimensions. Okay, maybe else. Okay, so the main theorem says the following, that this Z beta pi, which of course doesn't depend on beta actually, so it is nothing but, okay, so there I have to be a little careful, A plus B to the power M times the class of E pi, if you via the isomorphism here. So if you think of it as an element of this polynomial ring. Yeah. So that's the weak version of the theorem, the kind of boring version. And so I'll give you the stronger version in a second. But first, let me tell you why it makes sense to, yeah, exactly. Why it makes sense to extract a factor such as this one. There's something you might notice on such a picture. I could have said from the start, every line entering from the top at some point has to make a bend because it has to exit from the left or the right, right? So that means there are at least m bends on this picture, which means I could have told you from the start that always A plus B to the power M divides Z beta pi, because you always have at least m such factors. So, we're going to get rid of those factors. We don't like them. Okay, there's a geometric reason we're doing this, and this is somewhat tricky, so I'm not going to go there immediately, but anyway, so it makes sense to divide. You still get a polynomial, and the claim is that this is exactly the equivalent cohomology class, if you want, of this subvariety. Okay, and the way I actually derived this is a stronger statement, a geometric statement. So let me just state the statement. Maybe I'm not going to have time to prove it. And that's where the binary sequence is going to play a role. So for each beta, there is a partial Grobner degeneration. So I'll say a few words about what that means. Of E pi into reduced union. So let me check how I formulated it here. A reduced union indexed by blah 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 blah. Okay, yeah. A reduced union of well, let's just say a reduced union of varieties. I'm not going to speak to in such a way. Indexed by pipe dreams. So indexed by those little pictures. So yeah, those pictures. So indexed by pipe dreams with connectivities pi and binary string beta. Sorry, pi and binary string beta. In such a way. So maybe I shouldn't give them a name, F delta, indexed by pipe dreams delta with connectivity, blah, blah, in such a way that the class of F delta is exactly the weight of the pipe dream delta. So remember that a pipe dream has a weight, which is given by this big product here. So this big product over I and J of whatnot. So the claim is that I can now understand individually each term in this big summation as coming from one piece in the degeneration of my variety. And that's actually how I derived in the first place this, this theorem. Right? It's because I was playing around with Grobner degenerations. So there's a lot to say about Grobler generations. It's a fun game. You can do it. You can do it using a computer. You can put all these equations in the computer. And then you can try to ask the computer to degenerate the equations, like in some sense to kind of scale variables in a clever way, in such a way that it simplifies the equations. And sometimes things which are reducible, like e pi, will break into pieces. And usually in traditional algebraic combinatorics, the end game is to break things completely in such a way that you get what's called a Stanley-Reisner scheme, which means you want to degenerate the variety all the way to monomial equations, basically. So that's the final goal. And then you're done, basically, because then things are easy. But that's too easy. If there were, like here, this is not what happens. These equations, this is not a Stanley-Reisner scheme. That's why I insist on the fact that it's the partial Grobler degeneration. And that's why things are interesting, and that's why there's some interesting integrable system associated to it. That you get interesting varieties which you can analyze. You can still compute the cohomology classes, but they're not coordinate subspaces. So this does not form a Stanley-Reisner scheme. So there's some really interesting algebraic combinatorics associated to this degeneration. But I think I shouldn't talk too much about that because I realize I don't have, how much time do I have? 5 minutes. Perfect. So in the final 5 minutes, I want to talk a little bit about CSM classes and why this is relevant to. So one of the reasons that I did all this hard work is that I was actually interested in the so-called matrix Schubert varieties. So my interest in all this stems really from trying to understand better all the work on Schubert varieties, in particular, I really got started in this whole business in Moscow many years ago, trying to understand the work of Fomin and Kirillov on the application of the Yang-Baxter equation to Schubert varieties and stuff like that. And so this, you can think of this as a souped-up version of this really kind of old work, in which the integral model is kind of non-degenerate. So this integral model I just erased is actually a really nice, proper, integral model. It has all the features you expect, like invertible R matrices, whereas in the original setting, everything is a bit degenerate. And so here's one way you can see the connection. So yeah, I don't even know if I'm going to get to the Schwartz transform classes, but at least let me make a remark. There are obvious projections x, y goes to x, or x, y goes to y. It doesn't really matter which one you can choose. So let's say we pick the first one. Doesn't matter. If you do that, then e pi gets sent to something called a matrix Schubert variety, indexed by pi. Oh, and let me assume that, yeah, maybe for the time being, let me assume m equals n from now on, just to simplify the discussion. I would say would be completely true for m not equal to n, but I just have to add a few more words. So there's something well known to, yes, so let me assume m equals n, which means in this case, pi is just a permutation. Then the projection where you get rid of one of the variables is basically just telling you that you keep something which is called the matrix Schubert variety of pi, which is basically just a b minus b plus arbit closure. But pi here is the matrix of the permutation pi. So it's a very simple object which has been studied a lot, in particular in the context of a Schubert calculus, because it is closely, as the name suggests, it's just a slightly different way of expressing it's basically extremely closely related to Schubert varieties, which are things that we like. So it's kind of a matrix version, like a matrix. It doesn't mean it's more complicated. It's literally the same data as a Schubert variety, just packaged differently. That's the way I should put it. So in particular, so we a long time ago, for slightly different purposes with Alan, we developed a theory of leading terms of polynomials. So in particular, this projection, you can think of it this way: the leading term of e pi as b goes to infinity is nothing but the cohomology class of the matrix Schubert variety m pi. So as a corollary of some work of mine, but this is something anybody could have done, but we just didn't find the tools in the literature to analyze such things. So there's a natural way to interpret projections in terms of just taking the leading coefficient as a, so you take the highest power of b, you get a polynomial in all the other variables, a, x1, xn, yi, yn, so you get this thing, which lives in z of, so now we just have a, x1, xm, y1, yn, and actually a becomes actually redundant. You can essentially set a equals 0 for all practical purposes, and this is nothing but the Schwartz polynomial, right? So associated to pi, the double Schwartz polynomial associated to pi. So one of the ways you can think about this is that this is a theory of, like, as I said, subtype version of matrix Schwartz varieties and Schwartz polynomials. And the right way to interpret this, so you might wonder, yeah, but can we get rid of all this junk and just talk about matrix Schwartz varieties? Because this is the stuff that everybody likes. All the stuff you've talked about, lower upper scheme, nobody cares about that stuff. So how about we just stick to matrix Schwartz varieties? Can you express those polynomials directly in terms of those? And the answer is yes. And so the second big theorem of a paper says that z pi beta is also the so-called, okay, I'll cheat slightly. Let me just say the Chern Schwartz MacPherson class, because I'm running out of time, I'm going to skip a few things, but of exactly that cell, b minus p plus. So the open cell, the open orbit b minus b pi b plus. So there is a way of thinking about this z, even if you don't care about the lower upper scheme, entirely in terms of just very standard tools from like such as a matrix Schwartz varieties, or just orbits basically of the Borel group acting on the matrices basically. Thank you.
Let's thank Paul. Any questions?
You say that it's connected to some integrable model.
Yeah.
Can identify this some real hermeticisms like SL2 with skew to infinity or something like this.
Yeah. So right. So no, it's an AN model. So here I guess you could say it's an AM model to be very specific. This is an AM model because in a sense you have to keep track of the connectivity of lines. So every line is like a different state, right? So you have the empty state and then you have, so it has n+1 states, which corresponds to every possible line plus the empty state.
So it's GL m+1, kind of.
Right. So it's an AM model, but I haven't told you what the representation is. That's the interesting part. So the representation is, this is the C, it doesn't matter here. So I guess Cm+1 here, Cm+1. But then here you have an alternation of the representation, and it's dual. That's why you get this funny business. So for example, on this picture, you'd be like Cm here +1, and then Cm+1 bar. Well, bar meaning dual, right? And then Cm+1. Yeah.
But for IM model, you don't have this representation is n-dimensional. Not for any n. I mean.
No, this is just AM. So this is the defining representation of SL m+1, right? So, and this is all rational. Oh yeah. By the way, everything can be done. Yeah, I should also small remark. These are all rational models, right? So these are rational solutions of Yang-Baxter equation. So it's in this case associated to the Yangian of AM, and you can definitely generalize all this to the trigonometric world. Everything works exactly the same. And instead of doing things in cohomology, you do things in K-theory as you would expect. But things are a bit harder to prove. So anyway, these are technical details. But yes, you can do everything in the trigonometric trig world if you prefer that. So, well, I have erased the weights, but you can replace all the weights with the analogs, the trigonometric weights. Everything will work the same.
Did you consider grading questions, supersymmetric hermetices?
Supersymmetric matrix.
Yes. Supersymmetric hermetices, just replace.
Yeah, a lot of people have been asking me about that. Yeah, so my student, well, my former student actually, now he's defended. Ajit really wants to do something like that. Yeah, I'm not comfortable enough with the supersymmetric solutions. Well, the ones associated with superly algebras to understand what they mean geometrically. I know there's been some work on that, and I think this will be the next step, basically, I think, by now. By now, we understand really well all the sort of solutions associated to simple algebras and their Yangians or loop algebras. I think the next step is definitely to understand the geometry in the super case. I don't know how to do it. It's a challenge for the young folks.
I'm sorry, but I really don't understand what is extended generalized pipe dreams, because commonly pipe dreams are needed for one of the description of Schubert polynomials, Grothendieck polynomials, and so on. And it appears from analysis of 5 vertex models. Here you have 14 weights.
Yeah, so no, first I don't have 14 weights.
Correctly?
No, that's not the correct counting. So
what purpose of extended pipe dreams?
Well, okay, so if you want to think of the language of 5 vertices, then with the same counting here, you would get 6 vertices. So it's the non-degenerate model. See, the problem is the 5 vertex model is a degenerate model. We know that. It's a limit of the 6 vertex model in which you've sent some parameters to. It's not the most generic one. So if you want to think in this language, this is like going from 5 vertex to 6 vertex. And the question is, what is the geometric meaning? And of course, we kind of know already. There's a lot of work. Behind all this, of course, is looking the theory of stable envelopes of Koff and collaborators, and there's a lot of stuff there, but this is yet another variation on kind of the idea of, I don't want the 5 vertex model, I want the 6 vertex model if you want in this language of yours. And why 6? So you're saying there are 7, but actually, wait, I erased them. That's annoying. Yeah, anyway, no, there are only 6 vertices if you count correctly.
Okay, more questions? Anything from Zoom? No?
What you can say about Schwartz MacPherson classes? Is it decomposed positively in terms of I don't know, short function, Chern classes, or some positivity?
Yeah, you want to ask about positivity?
Application.
I don't know in general. This is a complicated question. Yeah, so the corresponding statement for Schubert varieties has been studied by Mihalcek and collaborators, and there are answers. There are positive answers. We know there are some positivity results. Here, the statement, this is a bit different. We're not taking CSM classes of Schubert cells. We're taking CSM classes of these orbits of B minus cross B plus. It's not exactly the same. They're related, but not directly. And in particular, I do not know any positivity result. That would be interesting to investigate. Yeah.
Okay. If there are no more questions, let us thank Paul again. Thank you. See you next week.